All right, well, hello everyone. So what we're going to look at here over the next few minutes are factors that are going to influence our resistance in our blood vessels. So resistance meaning the friction that our blood is going to encounter as it's flowing. And these things that influence resistance are going to then influence blood pressure as well, right? So resistance itself is the friction that the blood encounters due to the contact between the blood and the wall of the blood vessel, right? So that endothelial lining on the inside of the blood vessel, right? So there are going to be a few things that we're going to talk about that influence peripheral resistance, meaning resistance that the blood encounters in the periphery, so out in our blood vessels, right? Not in the heart itself, right? And the three main factors that are going to affect resistance are going to be blood's viscosity, the vessel length, and then the size of the lumen of our blood vessel, right? So as we go through this and we talk about these various factors, I want you to consider this formula here, right? So what this formula is, excuse me, what this formula is showing is F equals flow. Okay, so this is referring to flow. The delta P, so this triangle P, this triangle means delta, so delta P pressure. This means change in pressure, right? So in other words, as you have a change in pressure, blood is going to move from an area of high pressure to an area of low pressure, right? That's how fluid is going to move. It's going to move from areas of high pressure to areas of low pressure. The R in the denominator, this stands for resistance, right? So resistance causes a decrease in flow, right? So the way you think about this is flow is directly related to changes in pressure, because this delta P is in the numerator. So the bigger the change in pressure, the greater the flow. And flow is inversely related or indirectly related to resistance. So meaning as you increase resistance, you decrease flow, right? And vice versa, right? So the first factor that we'll look at for resistance and what's influencing peripheral resistance is blood viscosity, right? So remember, viscosity is technically a fluid's opposition to movement, right? So the resistance of fluid to its flow, the fluid's opposition to moving, right? So you can essentially think of this as like the blood's thickness, right? So the fluid's thickness. So think water versus honey or water versus syrup, right? Water is less viscous, it's less thick, if you will, compared to honey, compared to syrup, right? So there are a couple of factors, kind of two main ones that can influence blood viscosity. One is the formed elements or the things in the blood, right? So the particles in the fluid. So formed elements, so red blood cells, white blood cells, also things like protein, right? And so our blood is more viscous than water because there are more things, there are cells and proteins and other molecules in the blood that we don't find in just pure water, right? So if you increase the number of formed elements, you're going to change the viscosity, right? In which direction would you change it? So say we increase the number of red blood cells in the blood, that's going to thicken the blood, so that's going to increase blood viscosity, right? Think if you have something like polycythemia, right? Polycythemia is an increased red blood cell count that's going to make the blood more viscous, right? You can also have decreased red blood cells, so decreased formed elements. In that case, maybe something like anemia is going to decrease blood viscosity, right? And then it can also change with fluid, right? So your hydration status, right? So if you are dehydrated and you have less fluid in your blood vessels, that's going to result in thicker blood, right? More viscous blood, more difficult for it to flow, requires the heart to work harder, right? If you have if you have an increased hydration status, right? So you have more fluid in the blood, then that's going to decrease your viscosity, right? Make your blood less thick, right? Almost think of it as kind of like diluting it out, making it less viscous, right? The second major factor is vessel length, right? So how long is the vessel, right? So as you increase the vessel length, the blood in the vessel is going to be in contact with more vessel wall, thus increasing the resistance, right? So again, remember previously we talked about that resistance is due to the friction of the blood, right? Or that's one of the factors. So if you have a longer vessel and the blood is in contact with more of the wall, there's going to be more friction, right? And so think about this almost like a road, right? A road with vehicles on it, right? There's more resistance on. Imagine you're in traffic or something, right? You're in traffic on a very small road, right? And the traffic is half a mile long, or you're in traffic on a very large road and the traffic is 6 miles long, right? Well, the longer the road, the longer traffic is going to cause or result in more resistance, right? So in other words, you being unable to move your vehicle, right? So apply that to blood flow, right? If you have a longer vessel, then that blood is in contact with more of the wall, thus slowing its flow, increasing resistance, right? So this is relatively constant, right? So think of yourself, right? You're not drastically changing the length of your blood vessels, minute over minute, day over day, year over year, but they can change, especially with things like weight gain and weight loss, right? So increased weight gain um, uh, with an associated increase in adipose tissue, that adipose tissue requires additional blood supply, right? So additional blood supply forming new blood vessels is called angiogenesis, right? So angiogenesis, when you make new blood vessels, this prefix angio means blood vessel and genesis means like creation of, right? So creating new blood vessels, you're going to increase blood resistance, right? You're going to increase vessel length, which is going to increase resistance. If you lose weight, right, and you have less adipose tissue, and thus less blood supply servicing that adipose tissue, then you're going to have the exact opposite, right? So vessel regression, meaning the vessels disappear, they go away, and that decreases the total length of all of your blood vessels, decreasing the resistance, right? So viscosity, vessel length, and then vessel radius, right? So vessel radius meaning the the width of your vessel, essentially, right? And so with this one, what you'll see is that as you increase the size of the lumen, right, the radius or the diameter of the lumen, you're going to make it wider, and thus you're going to decrease resistance. So as diameter increases, you could also think radius, resistance is going to decrease and flow is going to increase. So this is why we looked at previously that formula. We said F equals delta P over R, right? And so the R, as you increase resistance, you're going to decrease flow, right? So in this case, we're decreasing resistance, so we're going to increase flow, right? So resistance goes down, flow increases, right? So with this, there's a ratio or kind of a formula that's sometimes called Poiseuille's law, which is essentially saying that as you have a kind of one-fold or two-fold change in vessel radius, you're going to have a 16 times change in flow rate, right? So in other words, as you go from a radius of 1 millimeter to 2, so you multiply it times 2, so twice as large, 1 millimeter to 2, you don't just get a 2 times change in flow rate, you get you get a 16 times change in flow rate, right? So again, you could look here, so you could plug in 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, right? So you get this massive change in flow rate, even with small changes in vessel diameter or radius, right? So this is the only factor that that we don't directly control it, but we have the most regulate. Our body has the most regulation, short-term regulation over vessel radius, right? The viscosity, over time, it's going to change a little bit, but it's going to stay relatively constant. Vessel length that we just talked about, it's going to stay relatively constant, right? Vessel radius, this is what is changing minute over minute, hour over hour, right? So how do you change the vessel radius, right? So you change the vessel radius through vasoconstriction and vasodilation, right? So whenever you constrict the vessel, you decrease the radius, you decrease the flow. As you vasodilate, you increase the radius, you increase the flow, right? So again, consider this. This is the one that we have kind of the most influence on, right? Now, you can also think of this in the case of, if you have atherosclerosis, right? So you have a development of, plaque in the blood vessel, then that's maybe decreasing the luminal size, the luminal diameter. It's making the flow go from this laminar flow, so again, this very nice smooth flow rate, to a much more turbulent flow rate, right? This would increase resistance, this would increase blood pressure as well, right? So again, consider some of these major things, right? Again, this formula that we looked at, flow is proportional to delta P, so change in pressure over resistance. And again, as the gradient changes in pressure, total blood flow is going to increase. So in other words, if you have a really, really high pressure in one area and a really, really low pressure in another, that's going to be a big driving force for blood to flow from the high pressure to low pressure. If you have small differences in pressure, there's still a gradient, but it's not as large, and so the flow rate isn't going to be as great. Right? And then our resistance, right? Our resistance is in the denominator, so it's inversely related to flow. So as we increase resistance, we decrease flow, right? And again, these factors that influence resistance we looked at: viscosity, vessel length, and vessel diameter, right? And so again, this is just another slide showing some of those same factors, and this is looking at it in the context of total blood flow, right? So again, total blood flow, pressure gradient, so that's the delta P, resistance, that's the R, right? So what increases total blood flow? Increase in cardiac output, so the amount of blood leaving the heart in 1 minute, right? And then less resistance, right? So less resistance, think viscosity, right? Less viscosity, so less viscous, less thick blood, right? Smaller blood vessels, right, in terms of length, right? So a reduction in vessel length, and then wider blood vessels, so vasodilation, right? If you decrease blood flow, it's exactly the opposite, right? So instead of an increase in cardiac output, a decrease, so less blood is leaving the heart, therefore less blood is going to be flowing throughout the periphery, right? That should make intuitive sense. And then all of the opposite factors from less resistance to greater resistance. So greater resistance, more viscous blood, narrow blood vessels, so vasoconstriction, and an increased length of our blood vessels, right, that we talked about, right? So these are all factors that influence total blood flow, right? So consider these, consider how these are related to, again, blood flow and thus blood pressure. And please reach out if you have any questions.